good at it. So something to look forward to there. All right, pitter patter. There we go. Hey, how's it going? Chemistry 3101. We're getting started off here with chapter 17. We did a little introduction last class. So I'm going to skip over some of the slides here. So let's see. Last class, what did we take a look at? We took a look at aromatic compounds, and we said that aromatic means stable. And so, yes, the first aromatic compounds were isolated from tree resins and saps and did have good odors. But there's plenty of aromatic compounds that are completely odorless. There's plenty of them that smell terrible. So it doesn't have anything to do with odor. It just means that we're dealing with a very stable compound. And we're going to actually talk about the stability of aromatic compounds in here. I said if you look at the structure of any prescription drug or illegal drug, you'll see that aromatic rings are almost ubiquitous. Okay, they're in most types of pharmaceuticals and illegal drugs as well. We talked about how coal, which is found beneath our topsoil, is laden with aromatic rings, and then there's other functional groups that are found in here, but it's largely comprised of fused aromatic rings, so aromatic rings that are joined together. Then we get into nomenclature, and we didn't finish this up, but we said benzene is the parent for a monosubstituted derivative. Yes, there's a few that you need to have memorized, but if it's not one of those common ones you need to have memorized, which I think is on the next slide, all you have to do is give the prefix and then follow it up with benzene. So if we have chlorobenzene, nitrobenzene, so you can imagine if we had something, let's just try a little something here. If we had this guy here, let's say we put an iodine on there. Could anybody name this compound? Or how do you think this would be named? Yeah, exactly. Thanks, Audrey. Yeah, Audrey says iodobenzene. Couldn't be more correct. So iodobenzene, yeah. Benzene. What if I put, could anybody try and name this one? And it's not a trick question or anything. You know how much I despise trick questions? Yeah, absolutely. All my students nailed that one. Yep. Yeah, isopropyl benzene, exactly. So isopropyl benzene is what you would call that. But this one also has a common name, and I'll tell you what it is. It's called cumene. It's not one of the ones that you need to memorize, but the reason I'm telling you is because this molecule shows up like Avogadro's number of times in our textbook. He loves to use this as a starting material in chapter 18 and 19 a few times. So just in case you can remember it, it's called cumene. But the ones that you need to know are these ones. In the last class, I said you need to memorize all of these. So if we have a methyl group on our aromatic ring or on our benzene, we call that a toluene. If you have a hydroxyl, we call that a phenol. If you have a methoxy group, we call that anisole. If you have an amine, we call that aniline. I went over cumene with you last class, I guess. If you have a carboxyl group, we call that benzoic acid. Some of you might have recrystallized this compound in organic 1. It's recrystallized from water. The next one, if we have an aldehyde, we call that benzaldehyde. Students usually remember that one quite well. The next one, if you've studied biology, you might have seen an acetyl group. So an acetyl group is when we have a carbonyl with just a methyl group attached to it. So we call this an acetyl group. And so this is acetophenone is what you would call this compound. And the last one is when we just have a vinyl group on here, we call that styrene. And students have asked before, if you take styrene and you polymerize it, you get polystyrene. Is that styrofoam? The original styrofoam was just polystyrene. However, now they add other compounds to it to make it less brittle and more stable and longer lasting, right? Good. Okay, so again, you need to memorize all those. And then we talked about the difference between phenol and phenyl, right, which is a common misconception. Students will get the two mixed up. So just remember, phenol is the name of a molecule. And just like we have methyl, ethyl, propyl, isopropyl, butyl, etc., when you have an aromatic ring regarded as a substituent, we call it a phenyl, okay, a phenyl. Okay, so phenyl group is when we regard a benzene as a substituent. I told you I will never use these goofy phi symbols here. That's never going to happen. But I love to use pH to represent an aromatic ring as a substituent, as a phenyl. Why? It's a great time saver, okay? And I like to maximize my time. Well, I said you also need to know the name of dimethylbenzenes. There are 3 of them, and I don't think I spent much time on this last class, so let's go over it here. Okay, we call these the xylenes, And if the two methyl groups are 1,2 apart from each other, we call that orthoxylene or orthosubstitution. If they're 1,3, we call that metaxylene. And if they're 1,4, we call that paraxylene. You can even shorten this to O. This is not a joke. You can shorten it to just O-xylene. You can shorten this one to M-xylene. And you can shorten this one to, you guessed it, P-xylene. Okay, they're all perfectly acceptable. The only time that we can use ortho, meta, and para is when we're dealing with di-substituted aromatic rings. If you have more than 2 substituents on your ring, just forget ortho, meta, para. You can't use them then. It's only for di-substituted aromatic rings. And if you're wondering, well, what makes those so special, di-substituted aromatic rings? Good question. It's because there's so many of them. Okay, there's so many different di-substituted aromatic rings that somebody developed this shorthand for nomenclature. So I think this is that question that I said, well, the answers are already posted in the notes. And somebody asked me about di-substituted aromatics. They say, do the 2 substituents have to be the same, or can they be different? No, they can absolutely be different, as you see here, right? The xylenes, they're 2 methyls. But here, let's say you have anisole, right? This would be our parent. If you remember this molecule here, and again, this is just review. This molecule here, if we have a methoxy group, right, that's called anisole. So anisole. And so the carbon that has the group on it of our parent, that's always considered to be carbon number 1. And so we have 2-nitroanisole, or we could call this orthonitroanisole. Then we have 3-bromotoluene. Again, right, why do we name it that way? Because the methyl group on our carbon, right, we have a methyl group in a toluene molecule. So we have 1, 2, 3-bromobenzene, or sorry, 3-bromotoluene or meta-bromotoluene. And the last one is para-chlorobenzaldehyde. Give me a thumbs up if you follow me on that. Or maybe I should say, are there any questions about, any other questions about ortho, meta, para? Because I want to try a couple with you. Of course, not ones that we've seen the answer to already. So I'm going to move ahead here and kind of go past the rules because we already looked at them. These are the molecules that were on the last page. So I'm going to skip this and go right here. Okay, so let's start with 17.1a. First question in the chapter. They give us this aromatic compound. Can anybody tell me what the parent is in here? And remember, cumene isn't one of our parents. It's not one of the molecules that you had to memorize, but there is a parent in here that you did have to memorize. It's not benzoic acid. It would be benzaldehyde, right? Yes, it would be benzaldehyde. So this here, this is benzaldehyde, and so we would regard this as carbon number 1. Now, whether we go clockwise or counterclockwise, all we're seeking to do is to give the substituent, this isopropyl group, the lowest possible number. Could anybody tell me, would I go counterclockwise or clockwise in this case? And it's not a trick question. Yeah, you'd go counterclockwise, right? Yeah, Audrey, absolutely. So 1, 2, 3. So we could call this 3-isopropyl benzaldehyde. That would work. Or could anybody tell me what the other name is that we could use since this is a di-substituted benzene? Or just give me the prefix, I guess. Yeah, perfect. Thanks, Tiana. Absolutely. It would be meta, right? Meta, or if Tiana just wrote M in the chat, there's nothing wrong with that. I'll just write meta here. Isopropyl benzaldehyde. Beautiful. There we go. All right, next one. What's our parent in the next one? Anybody? I know you know. Yeah, thanks, Maria. Perfect. Yes, absolutely. Couldn't be more correct. Yes, everybody's correct. So this is a toluene. Yes. So it's a toluene. So what would we call this? We'd call it orthobromotoluene. So I'll put O-bromotoluene, or we could call it 2-bromotoluene. 2-bromotoluene, both perfectly acceptable. And then the last one, can we use ortho, meta, para in this one? The very last one. No, we can't because it's tri-substituted. Could anybody tell me what the parent is in this one? What would our parent be in this guy? Yeah, thanks, Nicole. Absolutely, yes, it's a phenol. Yeah, perfect. And then okay, perfect, Sydney. Absolutely, everybody's 100% correct. Would I number starting from the hydroxyl group? Would I go clockwise or counterclockwise in this case? Yes, yes, you're all 100% correct, right? So I'm going to go 1, 2, 3 in a counterclockwise fashion. So I have 2, 3 dinitro. So 2, 3. No, sorry, 2, 4. My mistake. 2, 4 dinitro, dinitrophenol. Okay, there you go. Okay, so let's do one more. Let's just draw one out here. This is just a fun one that we'll do. So if I have an aromatic ring, if I put something like this, something like this, and something like this. What would be my parent in this molecule? It's tetrasubstituted. What would be my parent? Yes, absolutely. This is some kind of toluene. And so if it's a toluene, so we'll scribble this down here. Thanks, Diana. So I have one. It doesn't matter if I go clockwise or counterclockwise. I have substituents at carbons 2, 4, and 6. So I'd call this 2, 4, 6 tri. Could anybody tell me what the name of these groups are? NO2 groups? I know you know. Yes, thanks, Audrey. It's a nitro. So this is 2, 4, 6 tri nitro toluene. All right, there you go. I don't know if you can hear AC/DC in the background, but this is TNT. Okay, so if you've ever wondered about the structure of dynamite, there you go. Now you know. All right, trinitrotoluene. So that's TNT, an explosive. Okay, let's move on from there. All right, it's just like when I was in Boy Scouts. You know, what's the most interesting thing is learning how to tie the hangman's noose. What's interesting in chemistry is learning how to blow something up, right? Okay, well, let's move on here. It says for each of the following compounds, draw the structure. So I'll just kind of guide you through this one. We got 2,6-dibromo 4-chloroanisole. So I would start by drawing the parent. Right? I would draw the anisole molecule. So let's draw an anisole. It's going to look something like this. And then I would number the carbons 1, 2, 3, 4, 5, and 6, like that. So at 2 and 6, I have a bromo, 2, 6, dibromo. And what do I have at 4? I have a chlorine down here. It's not very pretty. There we go. All right, and the next one is meta-nitrophenol. I'm sure you could draw this faster than me. So first I'll draw a phenol. That, and we'll put a nitro group over here. Remember that meta is 1, 1, 3, right? 1, 3 substitution. All right, there you go. Give me a thumbs up if you're like, the nomenclature on this is actually not quite as bad as alcohol as well. Yeah, students usually like the nomenclature of aromatic compounds, and I don't blame you one bit, okay? All right, so let's move on. In last class, we talked about the structure of benzene, and I talked about some of these funny molecules in the upper left-hand or upper right-hand corner. This one here, oh jeepers, you'd have to fact check me on this, but I think the name of this compound was prismane or something like that. I don't know. They have funny names that I don't even remember. But the idea that I was trying to relay to you is that scientists knew that benzene had a formula of C6H6, but they didn't know what the structure is. And if you notice, there's something that's really wrong on this slide, right? And it was put there by the author of the textbook. Because Kekulé, he thought that what was happening is that there was an equilibrium between these two forms of benzene here, where it alternated double bond, single bond, double bond, single bond. So we know that this is in fact not an equilibrium, is it, right? These two arrows are a big time no-no. This was Kekulé's idea. This was not Mr. Dion's idea or Dr. Klein's idea. It's a big no-no. We know that it's not an equilibrium process, okay? You could write here, false, you know, it's not an equilibrium process. What's the name that we give to the two structures? How do we say they're related to each other? They're related by? Yeah, exactly. Starts with R, ends with resonance. That's right, resonance. Perfect. Thanks, Tiana. Absolutely. So we know that they're in fact resonance structures, right? And why do we draw, why do we draw structures like this sometimes? Well, it's to deal with the inadequacy of bond line structures, right? There's limitations, but we know that it doesn't actually alternate double, single, double, single. It doesn't do that. In fact, every single bond in the benzene molecule, every carbon-carbon bond, I should have said, has a bond order of 1.5. It's right in between 2 for a double bond and 1 for a single bond, right? It's right in between the two. And so that's why we use that. Now, Mr. Dion doesn't use this. It's not that there's anything wrong with that, so maybe I shouldn't have put an X over it. But this guy, your teacher is never going to use that because I find it's not really useful when you're trying to learn the subject. Okay, it actually makes it more complex. Okay, and it was Sir Robert Robinson, I think, that came up with this whole idea of putting the circle in the middle. So kudos to him, but I don't like using it because I don't find it's useful as an instructor. Well, let's move on to section 17.4. And this is kind of where we left off last class. We didn't really get into this in detail. So let's go over some of the concepts here. Now, I always try to tell you if there's some kind of, scary part or something coming up. I try to warn you ahead of time, like I tell my kids, like the dinosaur is going to come out here in Jurassic World or something, right? So I'm going to warn you that in this section we get into MO theory a little bit, but don't worry about it. I'm going to boil it down to the simplest possible bits of what you need to know. Okay, so don't stress when you see it. Okay, let's go all the way back to a happy time and a happy place in Chemistry 3101, in Organic Chemistry 1, when we studied the chemistry of alkenes, right? I know that you all remember this reaction. It's all near and dear to your heart. You take an alkene, you add bromine to it. It gives you anti-addition. You end up with trans 1,2-dibromo cyclohexane in this case. And so I know you all know this reaction off by heart. No stress at all. But what happens is if we have benzene and we try the same thing, we treat it with bromine, there's no reaction. And this is where it gets really interesting, because if you're saying, well, come on, there's a double bond here, and that's why it reacts, because pi bonds are weaker than sigma bonds. Why wouldn't this react, man? You've got 1, 2, 3 pi bonds. It should react like crazy. It should add 6 bromines, man. Well, in fact, it doesn't. And that's because, like I told you at the beginning of the lecture, aromatic rings are stable. Okay, can we get them to react? The answer is yeah. If you hit it hard enough, it will react. And that is really the focus of chapter 18, but we're not there yet. So why doesn't this reaction occur? And I went over the whole stability of benzene and actually quantified it here. So just to review, if you weren't here or if you don't remember this or if you didn't quite follow along, the idea is this. If you hydrogenate one double bond, okay, it releases 120 kilojoules per mole of energy. If you put 2 double bonds, it releases about twice as much. Okay, it's a little less because it's conjugated and there's some stability there, but it does go up considerably. And so if we had a theoretical molecule, this technically isn't benzene. They're saying this molecule is a theoretical molecule that doesn't exist. It's 1,3,5 cyclohexatriene. Well, anyhow, imagine it. It should have some kind of heat of hydrogenation around 360, but as you can see, when you actually hydrogenate benzene, you only release 200 kilojoules per mole. And so there's this stabilization energy that's associated with an aromatic ring. So now we're actually putting a number to it and saying, look how much more stable benzene is than we would expect it to be. Okay? And the way that we explain that is by using molecular orbital theory. So again, don't stress about it. I'm going to show you the very simplest bits. Okay. So let's think about this. If we look at the aromatic ring, I'm going to redraw my benzene molecule here for us. Okay, we know, I'm going to draw the circle. What the heck? I said I wouldn't, but I'll do it, okay? We know that we have 6 carbons, okay? Right? Okay, we have 6 carbons in the ring. Each one of those has an unhybridized p orbital on it, doesn't it, right? So if we look at our benzene molecule, okay, we know that every single carbon in there, they're all sp2 hybridized, right? So if it's sp2 hybridized, that means they all have an unhybridized p orbital. And that's what's being shown here. It's showing the p orbital on every single carbon in there. Okay, so going back to kind of your Gen Chem 1 days, if you don't remember this, I'll refresh your memory. If we have 6 atomic orbitals, 6 AOs, I'll just put 6 AO, okay? 6 atomic orbitals, remember that the number of molecular orbitals is always equal to the number of atomic orbitals. And if you're sitting there going, well, I don't remember that, well, I'm rehashing it for you, okay? So if we have 6 atomic orbitals, that means we have 6 molecular orbitals, okay? So 6 molecular orbitals. And remember that every molecular orbital can hold 2 electrons. Well, how many electrons do we have in the p orbitals? There's 1 electron in every single one of these unhybridized p orbitals. So 6 carbons, 1 electron in each. That means we have 6 electrons. Okay, now let's look at the MO diagram. So we have the 6 isolated p orbitals that have 6 electrons. So what happens is when we put our atomic orbitals together to make molecular orbitals, we end up with 3 that are anti-bonding. Those are higher in energy. And then we end up with 3 that are bonding molecular orbitals, and those are lower in energy. So now, since each one of those bonding MOs can hold 2 electrons, we start putting the electrons in those bonding molecular orbitals. And if we follow Hund's rule, the Aufbau principle, um, and Hund's rule, the Aufbau principle, and what's the last? Pauli exclusion principle, what we see is that all of the electrons, look, 1, 2, 3, 4, 5, 6, they all end up in bonding molecular orbitals. And when that happens, we say all electrons in bonding MOs. Therefore, we call this a closed electron, or we call it a closed shell configuration. We'll put here closed shell configuration. Okay. And that means that we have a stable molecule. Okay. So we're going to have an aromatic compound. Every electron is in a bonding molecular orbital. And therefore we have this closed shell electron, or this closed shell configuration. And so that's what imparts the stability. Now it says here the locations of the nodes, and as far as drawing the different molecular orbitals, that requires high-level mathematics. So I'm just going to move past that. You're not going to be asked to draw the different molecular orbitals. Then it says the delocalization of those 6 pi electrons in the 3 bonding molecular orbitals accounts for the stability of benzene. Like I said, it gives it that closed electron configuration. And so that is what imparts the stability of the benzene molecule. So maybe I should have put here closed shell. I didn't even write the put here. Closed shell electron configuration is what I should have put here. There we go. So closed shell electron configuration is what we call it. So let's go back here. All right. So now I'm going to pause here for just a second. So what we're going to do now is I'm going to take you on a journey. Okay. Oh boy, here we go. Okay, I'm going to take you on a bit of a journey. And what we're going to do is we're going to look at some very specific examples of, yeah, somebody said, uh-oh. I'm going to take you on a journey, and we're going to look at some very specific examples. So I'm going to get down to the nitty gritty a few times here, okay? And I'm going to try to tell you, like, this is a specific example you need to know. You know, this one is an example you need to know, okay? All right, so some of them you kind of have to memorize to start off with, and some of this is a little, it takes a while to straighten it out in your mind, but I'm going to do my best as your instructor to try to explain it to you the simplest way I can. Okay, ready? Here we go. Start now. Okay, so when we had our aromatic ring, our benzene molecule, remember that it alternated double, single, right? And I said, okay, we have a fully conjugated molecule here, and you said it's a aromatic compound. It has a closed shell electron configuration. It's stable. Everything's good. So based on that concept, you might look at a molecule like this, cyclobutadiene, or this cyclooctatetraene. They're both perfectly conjugated molecules, aren't they? Double, single, double, single. And you might look at that and say, hey, man, they're conjugated, they're in a ring, they're aromatic. And the answer is not so fast, okay? Neither of these compounds is aromatic. So let me just back up one more second, okay? Now, when it comes to looking at rings in this chapter, there's always going to be 3 possibilities. One possibility is for the compound to be aromatic. I'm going to scribble it down over here. Please make a note of this. So one possibility is for the compound to be aromatic. I'm just going to write A if it's aromatic. The other possibility is for it to be what we call anti-aromatic. Anti-aromatic. And for that, I'll write AA. Now, in fact, there are very few anti-aromatic compounds. You can fact check me on this. If you just do a Google search of anti-aromatic compounds after class, you'll see there's not that many anyway, okay? And then the next type of compound that we're going to look at is non-aromatic. Non-aromatic. Okay, and for that, we're going to put Na. Now, I'm trying to, go through my brain and think, like, what's the easiest way to do this? Anyhow, let's just leave it at that for now. So we've got three possibilities. Aromatic, right? Benzene is aromatic. And then we looked at this cyclobutadiene and cyclooctatetraene. Well, I said they're not aromatic. So if they're not aromatic, there's two possibilities. They can either be anti-aromatic or they can be non-aromatic. So let's go back on our journey and see if we can figure out what's the answer for both of these compounds. Okay, so here's cyclooctatetraene. Let me change this box to a red color maybe. Let's change this to red. There we go. So if we look at cyclooctatetraene, this molecule here, and you treat this with bromine, check this out. It actually reacts. So what does that tell you? It tells you that this molecule is not as stable as benzene, is it? If it reacts with bromine and benzene didn't, that just tells us that, hey, it's not as stable. And check this out. Cyclobutadiene is so crazy reactive that it reacts by itself. This is actually a Diels-Alder reaction. Yeah, this actually is a Diels-Alder reaction that's going on here. It's a cycloaddition reaction, and then it undergoes a rearrangement after that to form cyclooctatetraene. So the bottom line is, I mean, if you have this molecule by itself, it reacts by itself. Okay? It reacts with itself. So that means, I mean, benzene doesn't do that. Benzene is a very stable molecule. So what's the take-home message here? What this slide is trying to tell you at the bottom is that neither of these things is stable. Or sorry, is neither of them is as stable as benzene is, okay? That's the take-home message. So why would that be? All right, let's get into it here. It says, in order for a compound to be aromatic, aromatic compounds have to meet two criteria. And you're going to have to think about this very hard to figure it out in all the different cases. Number one is you've got to have a fully conjugated ring with overlapping p orbitals. It doesn't have to be a six-membered ring. It could be a five-membered ring. It could be a three-membered ring. It could be a seven-membered ring. That's not important. You've just got to have a p orbital on every atom in the ring, okay? Because you've got to have all those p orbitals overlapping in a circle somehow, okay? I shouldn't say a circle, but overlapping in a ring somehow. And the second one is that it's got to meet Huckel's rule, okay? So it says Huckel's rule is that you have to have an odd number of electron pairs, or 4n plus 2 total pi electrons, where n, which is just an integer, it could be 0, 1, 2, 3, 4, etc. I don't know why, but this part drives people crazy for some reason. So let's park it here on Huckel's rule for just a second, because I'm going to mix the two. Every once in a while, I'm going to bring up an odd number of electron pairs, and then sometimes I'm going to flip it the other way around, and I'm going to say just a Huckel number of electrons, 4n plus 2 pi electrons, where n is equal to 0, 1, 2, 3, 4. So let's zoom. Do I have enough room here? Let's just zoom in a little bit, and let's just use the formula. Let's put 0, 1, 2, 3, 4, something like this, okay? And we'll put n is equal to this, okay? And then we'll do 4n plus 2, okay? So let's just do a little bit of mathematics here. So if I have 4n plus 2 is my formula and n is equal to 0, what would I get for a number? So what should my number be right here? 4n plus 2. What's 4 times 0 plus 2? Thanks, Mary. Absolutely. I get 2. Okay, so that's 2 electrons, right? We're talking about total number of electrons here. If I have n is equal to 1, what's my number? 6, exactly, right? So then if I go to 2, I get 10. Then if I go to 3, I get 14. And then if I have 4, I have 18, okay? So this is the total number of pi electrons. But what else does it say? It says an odd number of electron pairs. So that's the total number. How many of something are there in a pair? There are 2 of something in a pair. Now, of course, I ran out of space here, but if you divide any of these numbers by 2, right, what do you get? You get 1, 3, 5, 7, 9. What do you notice about all those numbers in blue? They are odd, or are they even? Right? They're odd. So there you go. There's the answer. We either get a Huckel number, 4n plus 2, so these are the numbers, 2, 6, 10, 14, 18, or you can rephrase it and say an odd number of electron pairs, right? Because if you have a total of 10 electrons, well, how many pairs of electrons do you have? 5 pairs. It's like potato, potato, tomato, tomato, right? There's two ways of saying the exact same thing. Give me a thumbs up if you're with me on that. It gets annoying because and I don't mean I'm annoying, okay? It gets annoying because the book will kind of go back and forth between the two, and I'm guilty of it myself, okay? So now, if we look at cyclobutadiene, okay, I'm going to ask you a question. What is the hybridization of every single carbon in cyclobutadiene? What's the hybridization of all of them? sp2, right? You're all 100% correct. Okay, so all carbons are sp2. So what does that mean? They all have an unhybridized p orbital. So do we have a continuously overlapping system of p orbitals? Oh, you bet your bobby socks we do. Just a beautiful system, don't we? This thing is gorgeous. Okay, but how many pi electrons are in there? How many total pi electrons are in there? Are in this ring? 4, right? Because you have 2 pi bonds. There's 2 electrons in this pi bond and 2 electrons in that pi bond. Is 4 a Huckel number? Total number of electrons? No, it's not a Huckel number. Okay, or you could say there's 2 pairs, right? Either way, it doesn't satisfy Huckel's number. Does that, or Huckel's rule, does that make sense to everybody? Since we, right, you have 2, 6, 10, 14, 18. I'm sorry, my friends, but I don't see the number 4 in here. So this is not a Huckel number. Let me destroy all that. Okay, it's not a Huckel number. And so you can see that this compound does not follow Huckel's rule. And so now the question is, it's not aromatic. We know that. So is it anti-aromatic or is it non-aromatic, right? It's got to be one of those things. Okay, and we're going to come back to that in just a second. Now, I want you to look at cyclooctatetraene. Could anybody tell me quickly why this is not an aromatic compound? Why doesn't it satisfy Huckel's rule? Could anybody just scribble it down or unmute their mic? I'll make sure my microphone's up here. Can anybody tell me why this is not aromatic? How many total pi electrons do we have in there? Yes, we have 4. Exactly. Exactly. We have a continuously overlapping system of p orbitals. Nobody could argue with that. Every carbon in here is an sp2 hybrid, beautiful thing, okay? So we have a continuously overlapping system of p orbitals. Rule number 1 is met, but it's not a Huckel number, right? We have a number where we have 8, so that doesn't fit the Huckel number. We have 6 and 10 for Huckel, but we don't have 8 in there. And so now the question becomes, is this compound anti-aromatic or is it non-aromatic? You've got to make the call on this. Now, before we move on, let me tell you something about this situation. When you get into this situation and you say to yourself, well, that was easy, the compound doesn't satisfy Huckel's number. Well, now you've got to decide, is it anti-aromatic or non-aromatic? Okay, anti-aromatic compounds, we'll put here, super unstable. Okay, they're highly, highly unstable. And so here's kind of the Sparks Notes version. Are there anti-aromatic compounds? Yes, absolutely. There's some that haven't even ever been isolated. Okay, they've never been made by human beings. Okay, because they're theoretically so unstable. But the bottom line is, sometimes you'll see something and say, well, it's anti-aromatic. But here's the thing. If you have a compound that looks like it's anti-aromatic, a compound, look deep into my eyes, a compound will do whatever it can to get from here to here, right? Because this is unstable, but it's not as, well, actually, it depends on the molecule. But it's not going to be as unstable as an anti-aromatic compound. So that's why there's so few anti-aromatic compounds, all right? So let's get into these two compounds in a little more information here. So here's the, you could do that, Audrey. You could do that. That would be fine. But it doesn't always work, okay? Because we're going to look at compounds that have heteroatoms. So that wouldn't work that way. You can look at it sometimes, but not all the time. All right? And we'll see that when we get deeper into it. All right. So let's go back to our molecule, cyclobutadiene. If we have 4 atomic orbitals for our 4 unhybridized p orbitals, that means we make 4 molecular orbitals. Now, we always distribute them evenly. And so now we have a new situation. We have a bonding and an antibonding, but we have 2 non-bonding MOs. But the bottom line is, if you take those those 4 electrons, 1, 2, 3, 4, and you start filling in the orbital, starting with the lowest energy molecular orbital and going up from there, right? And of course, you have to abide by Hund's rule. What do you see? You have 2 electrons that are in a bonding molecular orbital, but 2 that aren't. And so we don't have a closed shell electron configuration. You could put here, lacks closed shell electron configuration. Okay, and since it lacks that closed shell configuration, this compound, cyclobutadiene, is in fact an anti-aromatic compound. So there you go, man. There's your first anti-aromatic compound. Now, I would memorize this if I was you. Anti-aromatic. Didn't I say I was going to abbreviate it as AA? I did, anyhow. All right, so we have an anti-aromatic compound. Now, if you look at the textbook, let me just see here. No, that's all I put in here. Okay. If you look at the textbook, he says, well, that compound, what it does is it tries to stretch itself out like this. It'll kind of flex like this, okay? So when it flexes like that, it prevents the p orbitals from overlapping, but it doesn't stretch far enough, and so the compound is still considered to be anti-aromatic. So somebody asked me a good question in the chat. They said, is it because it is conjugated but lacks closed shell? Exactly. So it follows rule number 1 as a continuously overlapping system of p orbitals, right, Tiana? Then we said it doesn't satisfy a Huckel number. So then we have 2 options. It's either non-aromatic or anti-aromatic. And I said that if a compound can avoid being anti-aromatic, it will. But in this case, there's nothing it can do to avoid it, and so it is considered to be an anti-aromatic compound. Yes. All right, does that make some sense? Cha? Na? Maybe the chat is slow. Anyhow, yeah, cha, all right. All right, well, let's move on from there. Okay, so that was example number 1. We're gonna see one right here, okay? So now if we look at cyclooctatetraene, we asked ourselves the question, is this a non-aromatic compound or is it an anti-aromatic compound? Well, if you look at the molecular orbital diagram, check this out, Tiana, right? You can see that not all of the electrons are in bonding molecular orbitals. Look, I have 2 that are in non-bonding. And so since it lacks the closed shell electron configuration, you would say, hey, this thing is anti-aromatic. But remember, I said a molecule will do whatever it can to avoid being anti-aromatic. And here's the answer. It turns out the cyclooctatetraene is so big that it can adopt a conformation or a shape where you don't get continuously overlapping p orbitals. You actually break the overlap. And if you're wondering, well, how the hell would you do that? Pardon my language. This is how you do it. What it does is, again, it can only do this because the ring is so big. And again, this is a specific example that I would suggest you memorize. Okay, this is a non-aromatic compound, and it's cyclooctatetraene. Okay, I would memorize this. It can adopt this tub shape. Okay, and what happens is when it adopts this tub shape, then it breaks the orbital overlap between the p orbitals. You can see that here and here, for example, and here, right? You can't have continuously overlapping, right? Because it breaks it. It breaks those pi bonds out of the plane on the bottom. Does that, give me a thumbs up if you see how that would break the orbital overlap. Yeah. So you see, like, you can't do this with cyclobutadiene. It can't do that. Can't adopt the tub shape, but with cyclooctatetraene we can. So again, I would memorize this. Okay, I would memorize this here. Memorize. So there you go. So now you have an aromatic compound, benzene. You have an anti-aromatic compound, cyclobutadiene, and you have a non-aromatic compound, cyclooctatetraene. So now you've seen all of them. All right, well, let's move on from there. And if you're wondering, could I make my own MO diagram? Like I told you, I will never, okay? You can record, I'm recording this. I'm going to post this to the interweave, okay? I will never ask you to draw an MO diagram and draw a bunch of lobes and all that stuff. It even said in the notes, it requires high-level mathematics to do that. However, there's a scientist by the name of Arthur Frost who developed something called the Frost circle, which allows us to draw a molecular orbital diagram for a compound to determine, or to help us, I should say, determine whether it's aromatic or not. And the frost circles, you don't need any complex mathematics to do it. It's just a couple of steps. So let me show you how you make your own frost circle to determine whether your molecule at least has a closed shell electron configuration. Okay, and this will work for, it'll work for a 3-membered ring, a 4-membered ring, a 5-membered ring, a 6-membered ring. Oh, please, a 7-membered ring. Can I draw this? Oh, screwed it up. 8-membered ring, etc., etc. So it'll work for any of these. Okay, rule or step number 1, draw a circle. Okay, check a root. I can do that. Step number 2, you inscribe the polygon. Could be a 3-membered ring. Here they're using a 7-membered ring, whatever. But you make sure that the bottom, or one of the points, I should say, let me underline this. One of the points, one of the connecting points is at the bottom of the circle. So that would be right down here. Okay. Then what you would do is you would draw a horizontal line everywhere that your polygon intersects the circle. So here we have a total of 1, 2, 3, 4, 5, 6, 7 points. Then you draw a line, a dotted line, if you will, right through the middle. Okay. Anything on top is a bond, or sorry, anything above the dotted line is anti-bonding. Anything below it is bonding. And of course, if you get something right on the line, we call that a non-bonding. Non-bonding MO. Sorry, it's hold the line. All right, that's the song. Anyhow, so let's see here. Let's move on. Okay. So frost circles help us to explain the 4n plus 2 rule, right? So if we have 4n plus 2, so 4n plus 2, and then we have n, maybe I should move this down here. There we go. So we have n is equal to 0. Son of a gun, where's my pen? 0, 1, 2, 3, 4. Let's just rehash this. We've already done it today. Let's do it again, okay? So if n is equal to 0, we have 2. If it's 1, we have 6, then we have 10, then we have 14, then we have 18. So check this out. If you start with a 4-membered ring, you have 2 electrons that are in bonding molecular orbitals. There you go, closed shell electron configuration, Huckel number, done. If you have a 5-membered ring, look, if you had all of the electrons in bonding MOs, how many electrons would you have? 6. That's a Huckel number. Same thing applies to a 6-membered ring and a 7-membered ring. They're all the same. I'm not putting these electrons in order, by the way, okay? So this one would be 2 electrons, right? These ones here, actually all of these, I should say. Anyhow, you get do you follow me on this? These ones here, okay? These all have 6, etc., etc. Give me a thumbs up if you follow me on the frost circle. Okay, we're gonna take another look at them like that. But there you go. That's really the whole thing. That's all there is to it. So note, the number of bonding orbitals is always an odd number. Aromatic compounds will always have an odd number of electron pairs. So Audrey asked a good question. She said, should I look for an odd number of pi bonds? And the answer is you can't always do that, okay? Let me show you an example, Audrey, why that wouldn't work. If you had a compound like, I don't know, like let's say you had something like this, okay? Let's say you have something like this. It doesn't have an odd number of pi bonds, right? It has an even number of pi bonds. This is called thiazole. Thiazole. But this compound is in fact aromatic. Okay, this is an aromatic compound. So you can't always go by the pi bonds. And if you're wondering, darn it, or you know, if you're, how does that work? Well, we're going to go over that in detail. All right, so frost circles. And so here is, you know, I usually print this out during the semester and I give it to my students just so they can have this in their mind's eye while they're practicing. So let's review again. If you have an aromatic compound, you've got a fully conjugated ring with overlapping p orbitals. It meets Huckel's rule. If you have an anti-aromatic compound, how do you know that? Well, again, you've got a fully conjugated ring. Let's just draw our cyclobutadiene, right? You've got a fully conjugated ring with overlapping p orbitals, but you have an even number of electron pairs, or 4n total pi electrons, where n is equal to 0, 1, 2, 3, okay? So 4n is an anti-aromatic number, or it's not a Huckel number. So when a compound fails criteria number 1, if it doesn't have a continuously overlapping system of p orbitals, it's considered to be non-aromatic. Let me give you an example of that. Let me just zoom in here, okay? So something really and I don't like to use the word simple in organic chemistry, but remember, criteria number one is you've got to have every atom has to have a p orbital on it, right? So let's say you had a molecule like this, where you have something like this. Well, that's non-aromatic. How do you know? Well, you've got an sp3 and an sp3 here, right? So you don't have a continuously overlapping system of p orbitals. Maybe not the best example in the world, but whatever. It works, okay? There you go. All right. So give me a thumbs up if you're even with me. I don't know, part of the like 50% of the way with me, because this is it's complex. I would say this chapter is complex. It's not long, but it takes some thought to get through it. Okay, let me see what I have next in my notes here. I just like to introduce stuff to you. Okay. Yeah, so Tiana, we're going to try to answer your question in a little bit. We're going to look at some specific examples right now. Okay, so now we're going to continue on our journey. Okay, and we're going to take a look at some compounds that can do certain things, to become aromatic or non-aromatic, et cetera, et cetera. Okay, so let's take a look at 6-annuline, this compound here. So 6-annuline is just a theoretical benzene, right? So that would be an aromatic compound because you have a continuously overlapping system of p orbitals. It satisfies Huckel's number. Now, if you look at 10-annuline, so look at this compound. Do we have a continuously overlapping system of p orbitals here? Yes or no? Could anybody answer that? Do we have a continuously overlapping system of p orbitals in 10-annuline? Is every carbon sp2? Yes, every carbon in here is sp2. So we have a continuously overlapping system of p orbitals, okay? Does it satisfy Huckel's number? Audrey, you could use your trick here because there's only pi bonds. There's no heteroatoms. Do we have an odd number of pi bonds? Right, does this satisfy 4n plus 2? Yes, absolutely. When we have, we'll put here n is equal to what? When n is equal to 2, right? Then you have a total of 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Done. So you would look at this compound and you would say, hey, man, baby, this is an aromatic compound. Done deal, okay? This is an example, and don't throw anything at me, okay? This is an example you have to memorize, okay? This compound is, in fact, non-aromatic. Okay, it's not aromatic. This one, I'll put here Na. It's non-aromatic. And if you're sitting there going, like shaking your fist at me and going, why in the hell? Yeah, exactly. Somebody put in the chat just like, what? As my daughter would say, what the? Okay. So here's the reason why. And you have to memorize this one. You see how you would have a proton here? Okay. We zoom in, you would have a proton here. Well, you'd also have a proton here. And they're like touching each other. Exactly, Audrey. So what this does is those two protons inside the ring are so close to each other that it pushes it out of planarity. Remember the tub, right? The tub pushed it out of planarity. So this pushes it out of planarity, and so it prevents the p orbitals from overlapping. So I'll even write that here. We'll put prevents p orbitals from overlapping. All right, there you go. And again, it's a very specific example that you'll have to memorize that one, 10-annuline. Now, Audrey, if we go to the next one, 14-annuline. 1, 2, 3, 4, 5, 6. Hold on. 1, 2, 3, 4, 5, 6. We have 7 pi bonds. Audrey, odd number of electron pairs. What do you think? Does this satisfy Huckel's number, 14-annuline? Yes, she said, yes, sir. Absolutely it does, okay? Now, Audrey, you can see that we have a proton sticking in here. There's one in here. There's one in here. And there's also one in here. And so 14-annuline is actually somewhere kind of in the middle. If you can, you're like, oh, come on. You told me there was 3 possibilities. I know, okay? I'm going to put an A on this compound, okay? Because this compound is actually kind of somewhat aromatic, okay? Because these guys do push it out of planarity, but not enough that it prevents the p orbitals from overlapping. So we're going to call this an aromatic compound, okay? There you go. So again, the 10-annuline is kind of a very specific example, just like the cyclooctatetraene was. And if you're wondering, are we done? The answer is no. I have some other very specific examples that I'm obliged to ask you questions about on the quiz. So just hold on tight and we'll get to them in just a sec there. All right. Any questions about the 10-annuline? I hope I explained that kind of to you. I had some good reactions in the chat to that one. And trust me, I agree with you. Okay, it's not a simple thing. Okay, well, let's move on from there. Let's take another, look at the Frost circles just kind of quickly. It says, could you have a 5-membered ring that's aromatic? Well, hell yeah, right? If you had 6 electrons in bonding MOs, then yeah, it's aromatic. That would work, sure. So what might be some examples of that? Here is a very specific example I want you to memorize, okay? I'm going to put here, memorize what we call the cyclopentadienyl anion. Check this out. Let me go back. Let me just go back here and just do a little something with you. Okay, let's just review a little something. Come on, we got time. If I have a carbocation, could anybody tell me, and it's not a trick question, I hate trick questions, what would the hybridization of the carbon with the positive charge on it be? sp2, couldn't agree more. Beautiful, right? Okay, now what if I had a carbanion? Okay, just something like this, okay? What's the hybridization of that carbon? And it's, again, I'm not trying to fool you or pull a fast one on you. It would be, thanks, Abishi. She's absolutely right. It's sp3, okay? So now what we're going to see is when you look at the cyclopentadienyl anion, right, Avicii, you've got a carbanion, except now it's not sp3, it's sp2. And if you're going, why would it do that? Because if it was sp3, you wouldn't have a continuously overlapping system of p orbitals. If this carbon adopted an sp2 hybridization, then we have a continuously overlapping system of p orbitals in the molecule, okay? And if this lone pair is participating in resonance because it's allylic to this pi bond, so can it participate in resonance? Well, hell yeah, it can. So now let's think about Huckel. We've got a continuously overlapping system of p orbitals. Check number 1. Then do we have a Huckel number? 4n plus 2, where n is equal to 1. 1, 2, 3, 4, 5, 6, aromatic. Okay, so that's why it adopts an sp2 hybridization. Because if it does, the compound becomes aromatic. What did I say aromatic meant? What's the simplest? Stabilizing, right? Exactly. And so if it can become more stable, it's going to adopt, I'm pounding on the desk here, it's going to adopt that hybridization. So that is why the cyclopentadienyl is taught to you in every other student who studies this course, okay? So you see that the lone pair is participating in resonance. How do you have a lone pair participating in resonance? If you don't remember chapter 2, let me remind you, okay? In order for a lone pair to be delocalized, it has to be in a p orbital. It's got to be in a p orbital, okay? If you don't remember that, pause the video, rewind it 10 seconds. The lone pair has to be in a p orbital to participate in resonance. So since we have all these resonance forms, it tells you that that lone pair is in a p orbital, okay? And so kind of the second thing that they love to ask questions about, and I've asked questions about this before, is if you think about an sp3, so imagine this carbon was sp3 hybridized, okay? And I'm talking about this guy right here. 4 signal bonds, you're like, sp3, man, that's all good, yeah. Well, an sp3 hybridized carbon-hydrogen bond has a pKa of like 50. It turns out that the pKa of this hydrogen, or one of these hydrogens, is actually 16. That's close to water. Why would it be so acidic, okay? The reason why this, one of these protons, okay, doesn't matter, they're just picking this one, okay? The reason why this proton is so acidic, remember, an acid is a proton donor. The reason this molecule wants to give up its proton is because it goes from something that is non-aromatic to something that is aromatic, and that's why it's so acidic. Give me a thumbs up if you follow me even part of the way on that concept. Really getting into it now. Yes, okay. Okay, again, it's a very specific example, but I know that I've asked questions about this. Dr. Anderson's asked questions about this, so it's not uncommon for us to ask questions about this. Let's do one more example, and then we'll take a break and we'll come back to, we'll go and take a look at some heterocycles, okay? Let me show you one more ion, and it's a a 7-membered ring with 6 pi electrons. So if you had 6 pi electrons in a 7-membered ring, where you have an empty p orbital and one of the carbons is a cation, it could be aromatic. Now, I'm sure that most of you looked ahead in the slides, and I don't blame you for doing that. But let's think about this. Let's just go slowly here. If I had this compound, okay, this is called the tropylium cation, and it's on the next slide. Just don't go there yet, okay? We'll look at it in a second. Every single carbon in here, what is the, okay, question number one, what is the hybridization of every carbon in this ring? Not a trick question. sp2, right? Every carbon in here is sp2, right? Because you know that a carbocation is sp2. So rule number one, do we have a continuously overlapping system of p orbitals? You bet your Bobby socks we do. Let me ask you this, does it satisfy Huckel's number? If somebody said yeah, and absolutely it does, right? 4n plus 2, where n is equal to 1. Thank you very much. 1, 2, 3, 4, 5, 6. Yes, sir, we do. So we have a Huckel number of electrons, and we have a continuously overlapping system of p orbitals. This, my friends, is an aromatic compound, and we call this the tropylium cation. So let's take a look here. The tropylium cation is an aromatic cation. So to review, we looked at the cyclopentadienyl anion, which is aromatic, and now the tropylium cation, which is an aromatic ion. I've been going on for quite a bit here, and I know I'm probably really into it, and you might be bogged down a little bit here. So now what I want to do is I want to take a short break, and when we come back, we're going to look at these two compounds. Pyridine, which you remember from, we've used it several times as a reagent when you made a tosylate or something. All right, we're going to go back and we're going to look at pyridine and we're going to look at pyrrole. And it turns out that both of these compounds are aromatic, but hold the phone. They're aromatic for very different reasons. Okay, now before we take the break, I'm going to tell you that in pyridine, the lone pair has nothing to do with aromaticity, but in pyrrole, the lone pair is required for aromaticity. Okay, it's involved in aromaticity. So again, we're going to come back after the break and we'll take a look at that.